Hi everyone, and thank you for having me present this educational session for OHBM. My name is Ashley Stewart, and I'm a researcher for the University of Queensland in Australia. This session is called Quantitative MRI for the Masses: How to Translate Cutting-Edge Methods in Quantitative Susceptibility Mapping to Neuroscience Applications. So what does this mean? Well, I thought we'd start by going over the goals of this session. By the end of this talk, we should be familiar with some of the challenges that hamper quantitative MRI workflows, like software setup, reproducibility, and others. I also want you to understand how recent solutions address these challenges, things like software containers and data-driven workflows. And I'd like for this to be practical. So by the end, you should be able to use and actually contribute to these efforts. Where and how can you access quantitative MRI software for your needs? And what does it actually look like when we apply this to some real data? And then hopefully by the end of the session, you'll be excited to include quantitative MRI in your next study. So as I said, we'll start by looking at the challenges facing the workflows. And since my background is in QSM, I'll be using it for most of my examples. In practice and at a high level, QSM has an acquisition step where we acquire MRI data, make sure to correctly combine and export phase data. We also have a conversion and standardization step where scanner images like DICOMs are converted into an analysis format like NIFTY or BIDS. Then we have our QSM processing steps, which in itself could include many computational steps, after which we'll have an analysis step where we look at susceptibility values in anatomical and disease-specific areas of interest. Now, these last three steps are really a computational pipeline. So let's think about how we could approach each of these steps practically. Well, the conversion and standardization step will usually involve writing scripts to convert images from DICOM to NIFTY, for example. There are other tools that our scripts might use, like DCM to NIIX or BIDSCoin. In the past, I've written different scripts for each data set that I've received from my collaborators. And this sort of scripting can be very tedious and error-prone and can change significantly depending on who they came from and how they were organized. You might also need Linux to use some of these conversion tools. The QSM processing step is usually done using MATLAB tools like STI Suite, MediToolbox, or Sepia Toolbox. You might also need other programs like the brain extraction tool in order to draw a mask for QSM. And while the MATLAB tools are often very user-friendly and let you quickly compare a few different QSM algorithms, they don't automate very well at scale for larger data sets. They require valid MATLAB license, and other algorithms for some steps of the processing may also require Linux. The final analysis step first involves segmentation, which can be drawn manually or automated using tools like FreeSurfer, before then being registered to the QSM space. This step will also often involve error-prone and tedious scripting, and as well as domain knowledge in segmentation and registration techniques, which can be quite challenging for new users. We also require Linux so that we can use FreeSurfer and other segmentation tools, while most MATLAB users tend to actually use Windows. So after seeing this full pipeline, the mix-up of tools that we may need, the need for scripting, licensing, and so on, the fact that Linux is a barrier for many users and is exacerbated by the fact that most of these tools aren't actually available in standard package managers. So you may have to download and manually compile code yourself, where you're likely to run into conflicting dependency problems, especially if you need specific versions of tools. You can really see how daunting this task can be and why it's such a barrier to new users of quantitative MRI. As reproducibility of neuroimaging analyses has become a growing concern, there's a huge need to develop solutions to these problems so that we can translate quantitative MRI to real applications. So I've identified a few challenges. Let's just start with one of them. How can we set up hardware and software for reproducible neuroimaging and quantitative MRI? Well, the organic solution to this problem that we see in many labs around the world is that people just buy different computers for different studies. This isn't cost efficient, hardware fails, studies have big problems, it's not very secure, these things aren't patched very well, and this is just a nightmare for an IT department. But this is how science is currently done. Let's consider for a moment the idea of a virtual machine as a possible solution. Let's say we have some hardware, a Dell Precision workstation running CentOS 6, and on it we've installed a hypervisor called VirtualBox. Within VirtualBox, we install a guest operating system, Ubuntu 16.04, which then has some libraries and neuroimaging software installed like ITK Snap, which we can use to view medical images. This highlighted part is the virtual machine, and we could write instructions to make this virtual machine reproducible to others, and the virtual machine could then be shared and downloaded by others to make it easy for them to have access to exactly the same environment. Now, the problem with this is that virtual machines have a big footprint. Because they virtualize the whole operating system, they use a huge amount of RAM, they take a long time to start, and they need a lot of disk space, which makes it much harder to store and then actually share them. Now, let's think about another solution. We still have our workstation running CentOS 6, but on top of this, we instead directly install ITK Snap into what we call a software container. So instead of virtualizing the entire operating system, a container virtualizes a layer called the user space and communicates directly with the host operating system using technologies called namespaces and C groups. Now, compared with VMs, containers have tiny footprints and are much easier to share. And this also means that storing many containers on one machine is much easier and actually makes this feasible. So instead of using a hypervisor, software containers use a container engine like Docker or Singularity to store, manage, and run container programs. And like VMs, these containers can run on any operating system. Okay, so containers sound great, but what if you don't have the time or knowledge to design or build software containers of your own? Well, luckily, the neuroimaging community has noticed these problems, and there are now a range of container repositories for all kinds of neuroimaging applications. Now, some of these containers, such as fMRI Prep or QSMXT, these automate entire processing pipelines for functional MRI and for QSM. Now, other containers like the FreeSurfer container and the AFNI container, they just make these specific neuroimaging toolkits available within a container across operating systems. Most of the popular neuroimaging software tools that you might use are actually currently available as containers through one of these software repositories. But if you would like to build your own or build one that combines a very certain set of tools for a pipeline, the NeuroDocker project generates custom container, Docker and Singularity container recipes specifically for neuroimaging. So for example, this simple command will generate a Docker container that is based on Debian and has FSL version 6 installed. So before we move on to the next topic, we'll stop for a quick quiz question. What is the difference between a container and a virtual machine? So is it A, containers are stripped back VMs with less features and less overhead? Is it B, containers virtualize an isolated user space and VMs virtualize a full operating system? Or is it C, containers keep your lunch fresh, but VMs don't? I'll give you a moment to think about this one. So hopefully we've landed on the correct answer, which is that containers virtualize the user space rather than the operating system. Of course, this means that they have much less overhead than a virtual machine, but they're not a subset of virtual machines. So moving on from containers, let's talk about workflows and the problem of making these accessible and reproducible for quantitative MRI. So here I have a folder, and this folder has some gradient echo data. We have magnitude and phase files as nifties, and we also have JSON files which contain some header information. On the left, we've opened a terminal window, and this terminal has been opened in a QSM container. So we have immediate access to a range of tools that are useful for QSM. So first, let's have a look at what folder we're in. And we can see that we're in the folder for subject 1. The same folder that we have open in this other window. And it turns out that this is actually just one subject of many. Now, because we're interested in QSM, we need to know some details about this scan, such as the echo time and the magnetic field strength, which each affect our computed susceptibility. So searching the header file for the echo time, we find that it's 20 milliseconds, and searching the header for the field strength, we find that it is 3 Teslas. QSM also requires a mask of the reliable phase signal, and for this, a brain mask is usually used. Well, since we have FSL installed in this container, we can use the brain extraction tool, or BET, to create the mask. And finally, to create the QSM result, we're going to use the TGV QSM algorithm, and this has a Python implementation that's been made available in this container. This command requires as inputs the phase file, the brain mask, the echo time, and the field strength. So after running this, we have our QSM result. So great, the container made it straightforward for us to run each of these programs without any installation process. But this workflow is not automated, and it requires domain knowledge to run. A container with some imaging software also doesn't describe the workflow in a reproducible way. Importantly, this won't scale very well if we have multiple echoes, sessions, or subjects that we want to process. And because it all runs using terminal commands, we could try to automate it by writing a script. But this, of course, requires some scripting skills. It's time consuming, and it might change depending on the input data structure, which may make it also difficult to adapt. Also, without other tools, scripting won't make this scale very well to large data sets, and will make poor use of the system's resources. So there's actually a recent solution to this problem, which doesn't seem to have a common name yet, but we could call this data-driven workflow systems. These actually solve the workflow problem by allowing you to design, automate, and share scalable workflows. And across each of these systems, there's a few common components. First, they each have a concept of an interface, something that knows how to interact with the underlying programs that you need for your workflow. Then we have an asynchronous directed graph, or a pipeline data structure. And this lets us connect our interfaces together as nodes, where the output of one node becomes the input to the next. And lastly, we have a run system. And this run system knows how to point the pipeline to some input data, and then generate, manage, and run each of the nodes as separate jobs. Now, because of this pipeline data structure, we have very straightforward scalability, since it implies which of our nodes can actually be run in parallel, and that can make it much better use of our system's resources. One final and optional component that I thought I'd mention that some of these tools actually have is compatibility with the brain imaging data structure, or BIDS. So BIDS is quickly becoming the de facto open standard for organizing and describing neuroimaging data. So using BIDS makes it much easier for people who use the workflow to prepare their input data in a very predictable way, rather than having to invent a new format for every tool. So there's actually a few of these workflow systems that you could use today to create pipelines, like Galaxy Project, which has been used in bioinformatics, Nextflow, which is used for computational pipelines more broadly, and NiPipe, which is specifically designed for neuroimaging applications, and already has many interfaces for common neuroimaging software available. In our terminal example, let's just focus in on one of the steps, where we use TGV QSM to compute the susceptibility map. So an interface for this, for a data-driven workflow, will understand the underlying command TGV QSM, and it will know what the required inputs are, and it will know the outputs. In the context of a larger pipeline, that TGV QSM interface can be used to create a node. And this pipeline actually represents exactly the workflow that we used earlier in the terminal. So our phase file is retrieved after matching it from a subject folder with an ID. The brain mask is generated using the brain extraction tool, or BET, and so on. And NiPipe can actually automatically generate graphs like this so that you can visualize your pipeline. I've actually created a workflow like this using NiPipe for QSM called QSM XT, which also includes some more advanced reconstruction techniques that reduce artifacts. So going back to our terminal, this time with our QSM XT pipeline available, we can run a single command to start the pipeline on a bids input folder. And it will automatically pass in the standardized folder and start running some jobs that run in parallel across the whole data set. You can see here that there are currently 6 jobs running using all 6 available processes, and there are 68 jobs ready. We can see at this particular snapshot in time that it's processing data across multiple subjects and sessions, and these final numbers indicate that it's actually processing across several echoes as well. So in parallel, we're actually calculating QSM, creating brain masks, and filtering for files all at once. By adding one more parameter, we can actually easily scale this to a cluster system like PBS graph. So this time the jobs are generated and submitted to the HPC system. So on to another quiz question before the final topic. What are the 3 main components of a data-driven workflow system? Is it A, coffee, snacks, and sleep? That's always a good workflow. B, Docker engine, software containers, and NiPipe? Or C, software interfaces, pipelines, and run systems? I'll give you a little moment to think about it. So the answer to this one is C, software interfaces, pipelines, and run systems. So these are generic components, and they're implemented in a range of tools like NiPipe, Nextflow, and Galaxy Project. So to motivate this final topic, let's recap where we're up to. So there's many neuroimaging containers, and some of them provide standardized tools, or standalone tools, like ITK Snap, AFNI, FSL, and so on, while others provide full quantitative MRI workflows like the one that we just saw. We know that containers and workflows are helpful for deployment and reproducibility, and maybe you could even go out and start using some of these now. But if you want to use containers for your day-to-day neuroimaging tasks and all your workflows and data processing in support of open and reproducible science, you still have to manage, update, and keep track of them. You need to have them ready where they can access the right hardware and data, and this can also be a challenge. So is there a solution to this problem? Well, in very recent years, cloud-based web solutions have been developed, and what we could also call self-hosted local environments that try to address this problem. So I've prepared a short table of some of these recent tools, like Flywheel and Qmenta, for instance. Flywheel and Qmenta are cloud-based services that store and process your data using containerized workflows. They have a big focus on collaboration between institutions, processing clinical trial data, and they also provide some proprietary AI technology for your analyses. A similar but open service, brainlife.io, is free to use and emphasizes open science principles. They have some cloud compute resources and data storage facilities available, but they also support you to self-host the computation while they provide the management and workflow tools. So a neat thing about BrainLife is that your projects can self-document their methods, and you can publish the reproducible results with DOIs that others can then cite. This last one, Neurodesk, was developed in my lab by Stefan Bollmann. And Neurodesk can be self-hosted, making it flexible to use local, cloud, or HPC resources, whatever you actually have available to you. And in a moment, we'll go over a practical imaging workflow for QSM that uses Neurodesk. So let's have a closer look at how it works. Well, when Neurodesk was designed, we wanted to make sure that it was compatible with Windows, Mac, and Linux. So it's containerized using Docker. We also wanted to make sure that it scaled well to HPCs and cloud resources. So a Singularity container is also available. We wanted it to be interactive and flexible, so it provides a full desktop interface. It had to be lightweight, so within this desktop, software is only installed on demand. And finally, we wanted to reuse existing technology. So we made use of NeuroDebian, Conda, and NeuroDocker as repositories and to build the software that NeuroDesk provides. So once NeuroDesk is installed, you can actually start it just using a Docker command. And then once you've started it, you can access the desktop interface using a web browser pointed to a localhost address. Once you log in, you can immediately access the desktop interface. And then within a menu, you have access to a wide range of neuroimaging software that is provided as containers and installed on demand. So for example, we could open ITK Snap if we wanted to view some medical images. So our final quiz question, why would we want to use neuroimaging software platforms? So is it A, platforms are the most fun type of video game? Is it B, to facilitate the collaborative management of data, workflows and computation in a reproducible and scalable way and support open science? Or is it C, to manage Docker containers for neuroimaging? So this may have been an obvious one, but of course the answer to this one is B. While different platforms have different features, they are all really there to manage your data, workflows, and computational resources in a reproducible and scalable way. So let's now consider a practical example. Let's say we have some inputs, some magnitude and phase data for 49 volunteer controls. We also have T1 weighted data, which we often need for segmentation. And in the end, let's say we want QSM for all subjects, as well as segmentations in the QSM space, which will help us derive some statistics for the areas that we're interested in. So how will we do this? Well, for this, we'll use QSMXT, our containerized QSM workflow, which we will run within NeuroDesk, our containerized imaging platform. This will be run using the Docker container engine running on some compute hardware, which could be an HPC, a workstation, or even a laptop. Now, I'll walk us through some of this process just to show you how this could actually be done practically. So in our machine running NeuroDesktop, we move some DICOM data to a shared location to make it available. Let's have a look at some of our data. We can see it's very poorly organized and inconsistent. We've got names like other, phase images, Wednesday, with some of these containing even more directories. So let's make our way back up to the top. And we'll open QSMXT from the applications menu. Then following usage instructions, we run a command to sort the DICOMs. As it recursively checks each folder and scans for DICOMs, they're sorted into folders by subject. And along with our subject folders, now we have a text file with all necessary citations for the conversions we've just done. And in each of our subject folders, we'll have a session folder, series folders, and finally our DICOMs. Returning back up to the top, we can now convert our data to bids, again following the usage instructions and running a command. Once this is done, our bids folder again should have our citations. There they are. And in each subject folder, we will have our each session, and then in anatomical scans, we'll have our gradient echo data. So opening a medical image viewer like ITK Snap, we can take a look. There's our input data. So returning again to the base folder, we can now start the QSM pipeline, again following the usage instructions and running a command. We can see this process that the NiPi pipeline is running. I've sped this up for the demonstration. Right. Now our QSM output directory will again contain all citations for the algorithms that we've used. And in an output folder, we have QSM for each subject, which again we could open using ITK Snap. So here finally are our QSM results. So returning again to the base folder, we can now run a command to start the segmentation pipeline. And once this segmentation pipeline finishes, we can open ITK Snap, view some of our QSM results, and then overlay the corresponding segmentation file. Wonderful. So adjusting the opacity, we can see the segmentation looks reasonable. Final step creates CSV spreadsheets for each of our subjects, which we can open in a spreadsheet viewer. And we can finally see susceptibility statistics for many regions of interest. And we could use these in an analysis to actually create figures for the group. So as well as being available in NeuroDesk, I created a page on Google Colab for this session so that after following this link, you can immediately actually try out QSM-XT directly in your browser without installing anything and using Google's computation resources on some test data, along with some common questions and answers. And so you can run the QSM pipeline from sorting DICOMs to then viewing results. So just to summarize before we finish, and this would be a useful slide to take a photo of once it's all visible. We've talked about software containers, which provide reproducible and deployable software for neuroimaging by virtualizing the user space. And for this, we need a container engine like Docker and containers that we could get from any of these repositories. We also talked about data-driven workflows and how they help us create reproducible and scalable reconstruction and analysis pipelines, relying on software interfaces, pipelines, and run systems. So some of the projects supporting these include Galaxy, Nextflow, and NiPipe, with workflows you could use like QSM-XT and fMRI prep. And lastly, we talked about software platforms for neuroimaging, which manage our workflows, computation, data, and provide collaboration tools. And this is possible because they provide an environment, hardware, cloud systems, and management tools. And here are some of those platforms. So thank you very much for your attention during this session. I hope that you all got something out of it.